Good morning. Thank you for joining the Industrial and Commercial Energy Demand presentation today. Industry includes some of the hardest to decarbonise sectors such as steel, chemicals and cement production. Fossil fuels in this sector are used for a wide range of activities such as producing very high temperatures, driving motors and are also used as feedstocks in some processes. The commercial sector includes subsectors such as education, health and hospitality. Much of the demand here is used for lower temperature processes like space heating and cooking. In this presentation, firstly, we'll hear the key learnings from this year's modelling. We'll then learn about the assumptions behind I&C modelling and the kind of levers that we pull in order to differentiate the four scenarios. We'll then have a look at what the I&C sector could look like in 2050 in terms of total energy demand, breaking this down into annual electricity, hydrogen and natural gas demand, analysing the shape of each scenario between 2020 and 2050. At the end, we'll recap the key learnings from this year's modelling, as well as discuss the main areas of uncertainty. Beginning with our key insights, we've condensed this year's modelling into four main takeaways. We'll expand on these points further throughout the presentation and have a recap at the end. So firstly, energy efficiency measures are a fundamental step in order to get to net zero. Secondly, decarbonisation of the I&C sector will require a diverse range of actions. Some industrial processes will not be fully decarbonised, even in net zero scenarios. And finally, industrial clusters of complementary technologies are part of the solution for net zero. We'll now move on to look at our key assumptions. So we've brought out the three greatest differentiating factors between the scenarios. The key differentiators are fuel prices, energy efficiency, and technology choice. Steady progression in the grey box is our least decarbonised scenario, and in fact it represents the credible least decarbonisation of the I&C sector by 2050. Due to the strong correlation between energy demand and energy prices, we've used the lowest energy prices in steady progression in order to encourage higher energy demand. We also have the lowest energy efficiency improvements in this scenario and a low fiscal focus on decarbonisation. This is the extent to which spending money on decarbonisation is a priority for the government and society. None of the UK's energy efficiency or decarbonisation targets are met in steady progression. This is in sharp contrast to the other three scenarios where the 2050 target is met. The route to decarbonisation in system transformation in the blue box includes an adoption of hydrogen-based technologies. A combination of low gas prices but higher carbon prices is therefore used in order to encourage the use of natural gas to produce hydrogen. The opposite approach is taken in consumer transformation in the yellow box here, where high gas prices are used in order to encourage electrification of industry. There are also significant energy efficiency improvements in this scenario, including an improvement by 20% by 2030. Finally, leading the way in our green box is the most decarbonised scenario. This scenario represents the credible fastest decarbonisation by 2050. Here, there is no preference between electrification or hydrogen as a method of decarbonisation. Both electricity and gas prices are highest in this scenario in order to discourage energy demand and incentivise energy efficiency improvements. Before moving on, I'd just like to mention that this year we have fixed GDP assumptions across all four scenarios. This means that no scenario is reliant upon strong economic growth in order to reach net zero. I'm now going to have a look at a total energy view of Great Britain in these scenarios. So in 2019, industrial and commercial consumers accounted for approximately 500 terawatt-hours of energy demand. This is more than a third of total GB energy demand. The current fuel mix is made up of electricity, natural gas, oil and other solid fuels. Around two-thirds of this demand is for fossil fuels, which will need to switch to a clean alternative in order to reach net zero. The three fuels that are part of the solution are hydrogen, electricity and biomass, which can replace gas and coal to provide heat for industrial processes. Looking at consumer transformation, second from left, due to significant electrification of industrial processes and space heat, consumer transformation has the greatest level of electricity demand in 2050. Energy in consumer transformation 2050 is around half of what it is today, and more than 30% lower than system transformation. This is due to electrification, but also significant energy efficiency improvements. Looking at system transformation, third from left, system transformation has the highest amount of hydrogen demand, and there is also significant hydrogen demand in leading the way, fourth from left. Despite having the greatest energy efficiency improvements to appliances, motors, and heating systems in leading the way, we actually see the least total energy demand in consumer transformation due to greater electrification. There is no oil or coal demand in the net zero scenarios, but there are tiny amounts of natural gas. All gas combustion in these scenarios is connected to carbon capture technology. Consumer transformation has the most natural gas compared to the other two net zero scenarios due to the lower availability of hydrogen. Finally, steady progression on the right has a similar fuel mix to today, the main difference being a change in the composition of gas. By 2050, there will be a blended gas made up of methane and green gases. There is also some substitution of oil boilers for gas boilers in steady progression. I'm going to look specifically at I&C electricity, and the chart shows I&C annual electricity demand in terawatt hours out to 2050. Overall, the assumption having the greatest effect is speed and timing of the deployment of new fuel switching technologies, switching fuel from gas and coal to electricity. I'm going to run through the chart in 7 stages from left to right. The initial divergence in 2020 is mainly due to fuel price differences before energy efficiency improvements begin to be implemented after 2021. A sharp drop in demand is noticeable in leading the way due to the sharp increase in electricity prices. We see a gradual uptake of commercial heat pumps in the 2020s, with the fastest uptake in consumer transformation, increasing electricity demand. This effect actually offsets the higher energy efficiency assumptions in consumer transformation relative to system transformation. Deployment of industrial fuel switching technologies, switching fuel from gas and coal to electricity, begins in 2026, with industrial heat pumps and electric boilers becoming available. These new technologies are essential in order to meet net zero. Energy efficiency improvements slow after 2030 for all scenarios as opportunities for such improvements lessen. Deployment of all other electric heaters and boilers begins, as well as electric tunnel kilns for use in the ceramic sector, begins by 2031, and the deployment of electric glass furnaces begins in 2035. We see much greater deployment of these technologies in consumer transformation, followed by leading the way. After 2040, we see a slight uptick in electricity demand in system transformation. This is caused by the increase in hydrogen storage. There is also further slowing of energy efficiency improvements from 2040. Around 2043, we see that electrification in leading the way outweighs the higher electricity prices and energy efficiency relative to system transformation. At the end of the period, we see a flattening off effect in leading the way as some of the fuel switching technologies begin to reach 100% deployment. Moving on to annual I&C hydrogen demand, we see very different rates of hydrogen rollout in these scenarios, with system transformation being the most hydrogen-heavy scenario. Hydrogen boilers begin deployment between 2026 and 2031 for use in industrial clusters. Commercial rollout begins in 2030 in line with the residential sector, with most of the hydrogen used in hydrogen boilers for space heating. Deployment of hydrogen glass furnaces begins in 2032, and deployment of hydrogen-fired kilns for use in the cement sector begins in 2035. Lastly, we have I&C annual gas demand. This falls close to zero in the 3 net zero scenarios, but stays relatively constant in steady progression. The range is driven by gas price and energy efficiency differentials before 2025, and faster heat pump deployment in consumer transformation, switching away from gas-powered heating, outweighs its lower energy efficiency relative to leading the way. Electrification of industry begins from 2026, and the shape of the decline between 2026 and 2050 is mainly determined by the speed of switching away from gas to electricity, hydrogen, and biomass. The last point to highlight before moving on to key insights is that CCS is used in industrial hubs to capture the emissions remaining from all methane combustion in 2050. So this year we have 4 key insights for our modelling. The first is all about energy efficiency. Energy efficiency measures implemented before 2030 are a fundamental step in our modelling to get to net zero. In consumer transformation, the high energy efficiency levels of appliances and the use of heat pumps reduces total energy demand to more than 30% lower than in system transformation by 2050. Our second insight is all around the diverse range of actions needed to reach net zero. Decarbonisation of the industrial sector will require energy efficiency, fuel switching, carbon capture, and negative emissions. For the commercial sector, it will need energy efficiency and adopting low carbon heat systems. Thirdly, an important point is that some industrial processes will not be fully decarbonised even in net zero scenarios. Regardless of the fuel used, some process emissions will remain due to the breakdown of raw materials in some processes. For example, in the cement sector, carbon is released when limestone is broken down. Finally, these process emissions mean that industrial hubs are more important and must include carbon capture technology. The hub and cluster approach reduces costs and risks for many potential CCS projects and enables carbon capture from small volume industrial facilities. On our final slide, we've highlighted the 4 main areas of uncertainty. First, our analysis assumes deployment of many new fuel switching technologies, energy efficiency and carbon capture technologies, which are currently untested on a large scale. Furthermore, we may even see new technology breakthroughs which have not been included in this year's modelling. Next, significant investment in expensive fuel switching technologies is essential for decarbonisation, but for the private sector to invest, there needs to be confidence that an appropriate policy framework is in place. This means that incentivisation in the form of carbon taxes or subsidisation of decarbonisation technologies is likely to be required in the near future. Finally, policy will be required to address some of the barriers to technology implementation, such as developing infrastructure for carbon capture and storage. So hopefully that's given you an insight into our anti modelling. I'll now hand over to Lauren Moody for the question and answer session.